Our first speaker in this session is the Reverend Dave Walker of Detectronic. He's actually worked in the flow survey industry for over 30 years, with experience of operating flow surveys in the UK and realistically globally. His work has been wide-ranging, from permanent flow measurement within the Mersey Estuary Pollution Alleviation Programme to short and long-term flow surveys in urban and rural drainage area catchments and sustainable urban drainage systems. Dave studied at Sheffield Hallam University, where his work focused on sewer flow measurement instrumentation and practices.
Okay, well, thank you very much, Oliver, for inviting me to talk and everybody else. The talk, as it states there, is dealing with the noise. I've got a couple of ground rules that have been given first from Oliver. Knowing that I'm a commercial director, I've got the first ground rule, that is no selling, no talking about Detectronic and our brilliant instruments and levels and flow monitors and the service we provide to the UK and global water industry. So I can't talk about that. And the second one is he knows that I'm a vicar priest in the Church of England, so I can't turn this into a sermon and I can't preach the good news of the kingdom to anybody either. So they're the two ground rules out of the way. So, and moving on from that, though, is one thing about sermons is I've always been told that keep it to about 15 minutes. So the slides are going to be, I reckon, I haven't practiced this, done a trial run, but we're around about 15 minutes. And then hoping that will actually open up a number of questions for discussion for all of us. Okay. So we'll start with this first slide. Dealing with noise, it took me back when I was putting this paper together, is been around about 5 years old in the 1970s. I don't know if anybody recognises this, but this is a TV screen from a cathode ray tube in the 1970s. Anybody remember back in those days? The young ones obviously won't, but they weren't probably around. But back in the 1970s, we were blessed with having 3 TV channels. And those 3 TV channels weren't always on. And when they weren't broadcasting, this is what you get. It was what's called white noise. And white noise is a raster of just noise moving up and down on the back of the screen. What was interesting to me right at the early age of 5, and excuse me for talking about my childhood and how exciting I must have been, but I'd sit and watch that raster. I'd watch that 1970s TV set, and then every time my mum had come close with a vacuum cleaner, the raster would change and get more vibrant. And then when she moved the vacuum cleaner away from the TV set, it's a change again. And I'm thinking, wow, the vacuum cleaner's talking to the television. Well, that's effectively what noise is about. It's about, and when I'm talking about noise, I'm talking about electrical noise, electrical interference. Well, noise actually is talking and being received, in that case, by the actual TV set. Couple of pieces of legislation, and I'm not going to bore us with this, but it's good to know that the Electromagnetic Compatibility Directive, otherwise known, abbreviated as EMC, that actually controls how we design and manufacture and deploy instrumentation, electronic instrumentation, into the wide world. And there's various tests we have to do there to, one, make sure it doesn't radiate electrical noise, and also that it doesn't actually receive electrical noise. Now, as strong as those regulations are, and there's been a lot of work over many years to develop that directive and the testing behind it, we do still have problems with noise being emitted and transmitted and received on a lot of our instrumentation. And whether that's an instrument in EDM monitoring, it could be in a sewer monitor, instrumentation on a wastewater treatment plant or pump station, there's always a lot of noise floating around. And I'm going to just touch on that and the principles behind that. The low voltage directive, again, is another directive what we have to comply with when considering how to design and manufacture instrumentation for the field. And I said I weren't going to delve onto that because that will take us a lot of time talking about legislation. But this is what I want to talk about at this moment is sources of noise. I'm not talking about the drums or the trombones and the musical noise. We're talking about interference and electrical noise from various other radiating sources. Pylon, for instance, those very large pylons can give up to 110 kilovolts of electricity. You only have to stand under one of those pylons, and when it's a damp weather like we are today throughout the UK, and you'll hear that electricity crackling as it's actually connecting to the water, to the atmosphere, to the damp atmosphere. So there's so much electrical radiation from pylons and electrical transmission sources. One on the right down there is AM transmitters. So this is amplitude modulation. You can also have frequency transmitters, which is radio stations, etc. I first came across this in Canada. Well, actually, no, it was in Australia first, and then it happened in Canada as well. We installed a D-Tektronix flow meter many years ago, 30 years ago, and every time we'd calibrate the level would just drift. And we just wouldn't understand it. It'd come back for calibration. We'd go on site and calibrate it, but the level would drift. I got to this particular wastewater treatment plant in Australia, and the perimeter fence of the treatment plant, metal fence, I put an oscilloscope on, attached it to the fence. And every time the person on the radio was singing, you could see the electrical noise change on the actual fence. The actual noise itself had a peak value of 2.5 volts peak to peak. You could light a small light bulb up with it. That's how much noise was being radiated. Just behind the trees at that treatment plant, there's a row of dense trees, was a radio transmitter. And that's what was happening, radio transmitter, transmitting the noise onto the perimeter fence coming and bringing that noise to our instrument. And in this case, it was bringing it back up through the earth supply. So it wasn't even radiating onto the actual instrument itself. On that, we have advanced over the years, and I'll touch on how we now eliminate some of that noise. But earth, having a good earth supply or a poor earth, as I've just explained there, can also create problems. So if you've got an environment, rural environment, and a very poor earth supply, but you've got noise penetrating around the area, it's very likely if you've got a mains powered piece of equipment, you could have noise coming back up through that earth and actually affecting, could be, if it's a level transmitter or a velocity transmitter, it could actually be affecting that. So we have to be appreciative of earth supplies when dealing with EDMs and mains powered equipment. Portable equipment, battery operated, tends to overcome that because you're not connecting to earth, so it's isolated from the earth itself. It's what's called double insulated as well, so we not have the same problem there. The one on the left, motors, switchgear, can also give us big problems. When you've got high voltage switching, that can actually just hit any power line and you just get a spike coming through. And the thing is with instrumentation, we're dealing with very low signals, and then we amplify them up. An amplifier in its nature will amplify the signal. If you've got noise coming into the first stage of that first 3-stage amplifier, then you're actually going to be amplifying the noise and not the actual true signal you want. So we've got to look at ways of eliminating that. And now EMC regulations actually work towards that, but are not foolproof by any means. So particularly installation where we can, you've got a great big power pump at the left-hand side there, the white box there, switch gear with a solenoid at the bottom. When that solenoid kicks in, that actually gives out quite a lot of EMF, electrical mechanical force, and can actually be picked up on instrumentation. Interesting in this case, it's not actually the instrument side of it, it's the actual earth supply, what's transmitting that noise down to the receive circuit, and then the receive circuit amplifying the actual noise as it transmits that high power voltage, that peak, when that solenoid kicks in and out. And it only happens every now and again. The other thing what we have to be careful with is CPUs are very susceptible to noise and switchgear to an extent that can actually just crash. So we, again, have to be careful where we're actually mounting equipment, even though we've gone through a number of EMC tests, etc., to shield our equipment. And that's what I'm going to just talk on the next slide, is how to reduce or filter out that noise. Yes, we can do it in electronics. So we can actually use what's called low pass filters or high pass filters. So that's frequencies. If you've got a mains source, a 240 volt or a 415 volt mains supply, what's causing you problems, well, that's going to be transmitting at a frequency of around about 50 to 60 hertz, not kilohertz, but hertz. So you'd want a high pass filter, i.e. you're going to block out that 50 hertz and then you pass forward any high frequencies. So that's basic electronics. And as any manufacturer for manufacturing level velocity flow monitoring equipment, that's not something new to these guys. That's what we do in the background anyway. We can also purchase low pass and high pass filters as well to put onto the actual main supply themselves. So that's another way of reducing it. As again, I'm showing the earth bar there. It's extremely important to make sure that you've got an adequate earth supply. And that might be, if you're actually in a rural area, driving in, not just one earth spike, but you may need up to 4 earth spikes. There's a lot of research done on earth bonding. And if anybody's experiencing problems with noise on instrumentation, mains powered instrumentation, then there's a lot of research being done on how to actually make sure you've got a decent earth bond. There's been a change in switchgear over the past 15, 20 years to make it more efficient. And what that has, there's been a knock-on effect of making the switchgear more efficient, is we get high voltage spikes when it actually switches on and off, or it actually changes its phase. So the earth supplies now have got to be much more robust than they ever were previously. Bottom left of that screen, we've got what's called a beaded core, a screened core. So you've got your cables in there, and you've got this beaded screen wrapped around that. Now, that's great. And what we have to do as electronic engineers is, as long as we put that screen to earth, that's going to create a Faraday cage around them core signal cables and protect them. Now, something what does tend to happen on the braided screen and connecting it to earth, if you're not experienced in earthing and screening of applications, you get this effect where everybody says, make sure you've screened it, make sure you put the screen to earth, and they screen both ends. Well, when you screen both ends of a cable to earth, you've effectively created yourself a very good antenna. And so you're not screening no more. What you're now doing is inducing and introducing more susceptible applications for receiving radio transmissions. You only have to read up about Marconi and what he did all them years ago. He made some fantastic antennas. And got to be careful that you don't end up screening both ends. So that is one of the other factors what we do tend to find in the field. If people are saying, "Oh, we've done all the earthing, we've done all the screening, and we've still got noise bouncing around our permanent EDM monitors, etc." Now, that what I've just talked about is electrical interference and how to overcome it and how to identify it. What I'm just going to touch on now for the latter 5 minutes of the talk is noisy data and what causes noisy data. Effectively, what causes noisy data is product limitations, is not understanding what the actual range of the product is for various applications. As I mentioned, as manufacturers, instrumentation manufacturers, we're all aware how to do EMC and how to reduce all that and what to look out for switchgear, etc., and telecoms. But this is actually now down to the users and the people that are actually taking the instrumentation and deploying it into their networks. So this is from a particular live site in the UK, one of the UK water companies. I'm not going to name which one it is. And this is noisy data, as you can see it. That dark blue line in the center there is actual true data. All this is what we call noise. And again, I reiterate, not electrical noise. This is where we've got, it's an ultrasonic level sensor, and I'm going to go on to that in a bit. It's where we're losing echo and it's giving wrong data. So this is incorrect data. The only way at this point now to get rid of that information is to have some clever tools within your software programs to actually start eliminating and actually effectively erasing them noisy spikes. So you're manipulating data. And that's what's been having to be done in many EDM monitors throughout the UK. Not all, but many. And certainly anybody from the UK water industry responsible for EDM monitors, I'm sure, and I'm not a betting man, but I bet you a few pounds here that they've seen data like that. That particular application is shown here as a schematic. The actual distance from the actual ultrasonic sensor to the invert is actually 2,515 millimeters. Well, this is a 3 meter range ultrasonic level sensor. So it's within range, but it is towards its level, to its maximum range. When we say 3 meters, we're only within 500 millimeters, if that, of the actual range of that sensor. It should still work. But if you look down on the left-hand side, Floa install, and this is the installation sheet on this particular site, it was turbulent. Now that's what's also causing and creating problems and giving us that particular data. And as I said, that particular data is from this particular site. And there you can see it. I think that's quite anonymous. We're not telling any tales here, but sensor slightly offset from the center of the invert. So you got potential of bouncing off an uneven surface of the actual channel itself. Turbulence, as I mentioned. Now, you can overcome that turbulence if you've got all that energy coming back to the ultrasonic sensor. So what you need to do there is actually mount the ultrasonic sensor much closer to the target of measurement, and that will actually give all that energy coming back and not be affected as much by turbulence of the actual flow itself. The limitation on that I'll touch on in a bit is because there's a deadband on an ultrasonic sensor, and the rate of rise could actually go into the deadband, and I'll touch on that in a bit. Wind and air movement, not majorly a problem in sewer networks, but when you've got a very large open channel, ultrasonic sensors are used extensively for monitoring the speed of air and wind movement. And those air movement sensors are transmitting and receiving at the exact same frequency, as it so happens, as the ultrasonic level sensors we use in our sewer network. So yes, wind and air movement can actually have an adverse effect on the signal being received. Temperature, I'll touch on that in a bit as well, is a big issue with ultrasonic sensors. Now, that's something we all know a lot about. So we've got some very clever algorithms and signal processing to overcome that. But I will touch on temperature as well. And again, finally, distance from sensor to invert, you're near on its maximum range in this particular application. Hence the reason why that photograph you can see there, and that installation is giving that data. So 4 limitations of ultrasonic level sensors, as I mentioned, 200 to 300 mil deadband. So by mounting the actual sensor in the, I'm going to run through this quick because Alistair McKinnon's coming on and he knows all about ultrasonic level sensors. So 200, 300 millimeter deadband is a typical deadband of where any water going into that deadband, then the sensor is what we'd call blind. We have improved, and when I say we, the instrumentation manufacturers of ultrasonic level sensors are improving that deadband and the angle of spread, beam spread, which is at the bottom there. 1 in 5 beam spread typically. So at 3 meter range, you're looking at 600 mil beam spread. Again, we are improving the angle and the beam spreads, but let's stick here with the traditional ultrasonic level sensors. Wind speed, as I've just mentioned, 40 to 200 kilohertz is the ultrasonic sensors used for wind speed. So in large open environments where you've got wind passing through that beam, then that will also create noise and interference on that ultrasonic sensor. And the final one on that slide is surface foaming, fogs, etc., fats, oils, and grease. They have a tendency to absorb the ultrasound and the energy. What we need is that energy hitting the actual target of measurement and returning back to the ultrasonic sensor in one go. And the only real way to do that is, well, 2 ways, is either increase the power, which can cause a couple of problems because you've got, if it's a battery operated system, then you've got limitations on power and longevity of life before changing the batteries. But also, if you increase the power too much, you have what's called ringing effect. And I've got a slide showing the ringing effect in a bit. So you can't increase it too much. The other way is to actually lower the sensor much closer to the target of measurement, so you're getting all the energy focused and returning back to the ultrasonic sensor itself. But again, the limitation of placing an ultrasonic close to the target of measurement is that deadband. At once the water, there's a surcharge conditions, and it goes into that deadband, then the ultrasonic sensor is blind. Temperature, I just touched on it slightly there, but you can see here that just a 5 degrees change in temperature. The table on the right is an 8 meter transmission. So at 8 meters, you've got a 75 millimeter error in the target measurement. Same error associated with 5 degrees centigrade on the left if you're within 800 millimeters of measurement. As you can see there, the actual error in level reading is much less. Now, temperature is something we all are well aware of, and we do some very clever adjustments within the circuitry, within the ultrasonic sensors out there in the market. But when you're at such a distance of 8 meters, if you're monitoring the temperature in close proximity to the actual ultrasonic sensor, to actually know the actual change in temperature throughout that column of air, i.e. 8 meters length of column of air, then you need to know what the changes are, or that will also give you inaccuracies. So again, actually, if that ultrasonic level sensor, and I keep using ultrasonic level sensor because it's a fantastic tool in sewer network monitoring, EDM, it's non-contact. It's non-contact, so it can be brought very close to the target of measurement and actually not interfere with the actual flow itself. So ultrasonic signal, echoes, we can have. So here, what we're showing here on the right is the ringing, which is that big, large area at the beginning of that plot, and then you've got multiple echoes. Now you'd think and like to appreciate that this larger echo down here is your true signal, but it isn't. The large echo is here at the start. And you've now got to develop algorithms to actually say, is it this small echo here? Is it this echo here? Or is it this very little one down here? What's the true echo? Now, in a laboratory, in our test rigs, we know which echo it is because we're there and we're seeing it. Out on site, that instrument is relying on the clever technology and the algorithms behind that to actually interpret that graph, that data plot there. So that's what we're up against. And I'm not saying that we don't do that, because some of the ultrasonic level manufacturers on here have been doing this for years, as well as D-Tektronix. So we've learned a lot about that and how to process that. But if those echoes change and they vary because of any noise or whether that's turbulence or anything like that, that's what gives us that. I'm just going to quickly run back to it. That particular plot there, that is what we will get when we don't understand that interpretation. Okay, so things what we have to look out for, which are pretty standard and straightforward in a chamber: channel benching and pipe radius, what may actually refract the energy coming back from the sensor. Step irons in the way, mechanical electrical screens, as I mentioned earlier on about electrical noise, turbulence, surface foam, loss of echo, air movement if it's a large open channel. Loose access covers. Yeah, we're dealing with noise here. So you've got a loose access cover and it creates a big bang. Then what's that going to do to our sensors in the sewer network? So mounting ultrasonic level sensor in close proximity to the target of measurement. We've got a comparison graph there. The red line is the traditional ultrasonic red sensor, and the blue line is where we've actually mounted the sensor in close proximity to the target of measurement. As you can see there on the level, the ultrasonic level is actually below the spillway at that point, but within close proximity. The advantage of what we got there is what Andy Godley touched on earlier in his talk as well, is actually we're still able to pick up that valuable data in dry weather conditions. We can pick up the diurnal patterns, and the information, what we can gain from that, can actually help us in helping with the forecasting and the algorithms and the fuzzy logics and all that data analysis, what has to go post-processing. So the closer we can mount our ultrasonic level sensor to target of measurement, keeping it focused, getting that energy back is the way to go. And you can see that as the comparison of the data there on the right-hand side. The red data is the traditional ultrasonic level sensor with that spiking, as we saw earlier on, that noise. If you've got that red data, you've got to try and pre-process that and actually try and get rid of all that noise in that background, what's just distracting from the true reading. So final slide, summing up. Check your environment for sources of transmission, EMC, frequency and voltage. In fact, I've got an app on my phone. It's an EMC tester. It's a free app. So you get a shed load of adverts about what to buy your wife for Christmas or a partner for Christmas. As long as you get over that bit, it's pretty good. I walk under a pylon and you can see it go off at scale. So it's a good app. What we also do within D-Tektronix is we carry a portable oscilloscope, and that also allows us to actually pick up noise and any interference, what we might be receiving from electrical background noises, etc. And at the bottom, check the application. Is the product suitable and is it in range for what you're wanting to achieve? Okay, if it's just a on-off, you might get away with it, but if you want that reliable data, that background data, make sure that you're within range. Okay.